Chapter 3. Measuring the Signatures of Reality. To understand what geometry hyperbolically structures the universe into being, we must measure the intrinsic traits of that structure, the constants of nature. Each constant represents a specific kind of symmetry, a persistent ratio, a fixed relational scaffolding embedded in the fabric of physical law. Every unique characteristic is a fingerprint of the manifold we live in. Measuring them marks our first glimpse into the hidden geometry that structures the world. These constants are the signatures of the hyperbolic stage we are trying to understand. As Lord Kelvin once remarked, when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. Or as James Clerk Maxwell observed, the most important thing a scientific man can do is to make measurements. More important than solving the equations is knowing the values to plug into them. Every constant of nature is a clue, a whisper from the architecture beneath. Each of these constants has its own discovery story, an account of how it was pulled from the world by curiosity, ingenuity, and measurement. Let us trace how a few of these were found, beginning with the speed of light, c. It is easy to forget that for most of human history, light was assumed to move instantaneously. No delay, no travel, just presence. That illusion was broken not by conjecture, but by observing something about the moons of Jupiter. In 1676, Ole Romer, while charting the eclipses of Io, noticed a strange variation. When Earth was approaching Jupiter, the eclipses arrived early. When Earth was receding, they arrived late. The only explanation was that light took time to travel. Its speed was finite. That was the first chisel strike against an ancient belief. Romer had revealed the delay, though not its pace. Then came James Bradley, who noticed that the stars appeared to shift position as Earth moved. The effect, known as stellar aberration, hinted at Earth's motion through a sea of finite-speed light, and with that, a second chisel strike. By the mid-1800s, the race to measure light's velocity had become a contest of ingenuity. Hippolyte Fizeau fired light through rotating gears. Leon Foucault bounced beams between mirrors. Each measurement drew the veil back further, slowly revealing its number to higher precision. But it was Einstein who gave the number meaning. In his theory of special relativity, c became the invariant, the speed of causality, the structural ceiling of motion, the fixed ruler of all frames. It was no longer a property of light. It was a property of space-time itself. Today, we don't just measure the speed of light. We define two atomic bases, the meter and the second, in terms of it. It is built into our most basic grammar of the world, an anchor point in the architecture of what is. If the speed of light defined the scaffolding of space-time, then the reduced Planck constant revealed the granularity of action, the quantum tick of the universe's internal logic. At the dawn of the 20th century, Max Planck was wrestling with a puzzle. Why do hot objects radiate light in the way they do? The equations of the day could model the low-frequency end of the spectrum, but at the ultraviolet end, the theory exploded into infinity. It made no sense. The math failed where reality persisted. So Planck did something bold. He asked, what if energy itself comes in packets, discrete steps rather than a smooth slope? He introduced a constant, h, to define the size of these steps, tying energy directly to frequency. It was a desperate move, a trick to make the math behave, but it worked. Too well. The blackbody spectrum snapped into alignment, the ultraviolet catastrophe vanished, and a door creaked open that would never close again. That constant, h, and its reduced form, h-bar, which equals h divided by 2 pi, didn't just solve a thermodynamic mystery. It unveiled something deeper, that nature itself operates in quantized steps, that between one state and another, there is always a minimum unit of change, a graininess to the world that is not due to limitation, but structure. Einstein used Planck's idea to explain the photoelectric effect, showing that light itself could be thought of as a stream of quanta, photons, with energies set by h-bar. Later, Niels Bohr used it to explain why electrons orbit at specific distances, and Schrödinger built it into the wave function that describes matter itself. The entire edifice of quantum mechanics is suspended from this one idea. h-bar is a structural constant. It defines the quantum of action, the smallest possible unit of interaction, of change across time. To act is to transform, to move from one configuration to another. h-bar tells us how much action is required for such a transformation to even exist. It is the price of change in the universe, the toll paid at every turn of quantum evolution. As measurement techniques advanced, from atomic clocks to quantum Hall experiments, our knowledge of h-bar grew sharper, but its presence was always more than numerical. It was ontological. It said something about how the world must behave if it is to endure through time, structured by rule. h-bar is a threshold. Below it, persistence becomes undefined. It is the clearest sign we have that persistence itself is quantized. Where C sets the structural ceiling of causality, and h-bar quantizes action, the electron mass anchors the architecture of matter. The electron is the first truly elemental particle we encountered, glimpsed in the flickering shadows of cathode ray tubes. In the late 19th century, J.J. Thomson was studying the glow inside vacuum tubes, curious about what made the phosphor walls flash. By bending the rays with electric and magnetic fields, he measured their charge-to-mass ratio. The result was astonishing. Whatever these particles were, their mass was tiny, their charge significant, and their behavior followed precise, quantifiable rules. He had discovered the electron, not by sight, but by inference. It revealed itself through geometric deflection. But to know its mass, we needed another step. In the early 20th century, Robert Millikan performed his famous oil drop experiment, suspending tiny drops in an electric field. By adjusting the voltage until a drop hovered motionless, he could deduce the electron's charge. Plugging the value of that charge into Thomson's ratio gave the first glimpse of the electron's mass. That number has become one of the most precisely known quantities in all of physics. It determines the structure of atoms. It sets the scale for chemical interactions. It decides how matter persists. This mass defines how tightly electrons cling to nuclei, how photons scatter off particles, how fields curve around charge, and it is one of the constants that geometrically calibrates reality into Dirac's coherent system. According to the Dirac equation, the speed of light, c, the reduced Planck constant, h-bar, and the electron mass allow quantum systems to stabilize, to hold form, to remember their identity across time. These are not just numbers. They are scale setters, the gravitational centers around which quantum coherence curls. They are the silent sculptors of everything solid, the first whispers of matter made persistent. Every measured constant of nature anchors our theories, constrains their freedoms, and reveals the contours of a manifold beneath atomic logic. The Committee on Data for Science and Technology, CODATA, maintains the most precise values of these parameters. Their list of constants, drawn from global collaboration and experiment, represents the finest glimpse we have into the quantitative structure of the universe. What follows is the complete list of the constants of nature as curated by CODATA. These are the numerical relics of the manifold we inhabit, its structural resonances, frozen into form by symmetry. Each value has been refined through generations of experiment, and together they constitute the most precise empirical mirror we have ever held up to the underlying logic of the cosmos. There are exactly 288 of these constants. That number might seem arbitrary now, but it isn't. It hides a secret symmetry we'll soon uncover, one tied to the hyperbolic figure 8 knot. Look closely. You will notice that the second, meter, coulomb, Kelvin, and kilogram appear again and again in the names of the constants. Note, Hertz equals 1/second. What follows is a sacred text, the full vocabulary of nature's internal logic. Like any new language, it at first appears as noise, but with the right lens, pattern emerges. The constants of nature do more than set magnitudes. They ensure that the units we use, second, meter, coulomb, Kelvin, kilogram, interact without contradiction. They enforce coherence across different domains of measurement. Their values are reflections of deeper geometric structure holding that system together. What follows is a detailed account of discovering the logic that connects these 288 constants, the empirical skeleton of reality. Part 2. Discovering the pattern beneath the constants of nature. Chapter 4. From Measurement to Manifold. Before explaining how the pattern was discovered, let's first see it, or at least part of it, so it becomes clear that we are talking about revealing a pattern in the constants of nature that is so stark that it can be recognized even without knowing what the symbols mean. To make this pattern visible, we lay them all out. Every constant, written as a structure formed by combinations of plane boundaries, all partitioning and connecting according to the same two rules. Every expression is constructed from the same foundational ingredients. The result is a grid, 8 columns of 36 equations each, making 288 expressions, all bound by the same syntax. These algebraic geometric connections are structural expressions of a deeper grammar. What follows is one vertical slice of the full grid, a single column composed of 36 algebraic geometric expressions, each characterizing a constant of nature. Don't worry about decoding every part just yet. What matters is the structure, the repeating pattern, the shared syntax, the consistent ingredients. Beneath each of these constants lies an iterated complex exponential, I to the I to the I to the I to the I, and so on. This is known as the infinite power tower of I, the imaginary unit. The powers of I trace out a spiraling structure in the complex plane that orbits and converges on a single fixed point, hovering between the real and imaginary axes. When iterated infinitely, this power tower stabilizes into a value that represents a kind of equilibrium between opposites, a balance struck between real and imaginary, order and oscillation. That this same spiraling structure appears again and again underneath the surface of each constant in this column suggests that nature's energy architecture is patterned by the logic of complex iteration. The infinite power tower of I reveals itself as a bridge between algebra and geometry, chaos and form, a deep thread of structure connecting what otherwise appears to be disparate constants. These constants are echoes of a single process, each ringing out from the same recursive drumbeat. At first glance, the constants of nature are an eclectic catalog of quantities. Some have dimensions of mass, charge, energy, while others are dimensionless, representing gyromagnetic ratios or magnetic moment ratios. Some have enormous exponents, others minuscule ones. But when we reframe these constants in terms of Planck boundaries, a different picture emerges. The constants of nature are constructs of 5 modular geometric limits, 5 Planck constants, woven into one coherent system via 2 fundamental structural rules. We will go through this in detail later. The first rule enforces invertibility, ensuring structural balance throughout the system, guaranteeing that no transformation breaks the principle of persistence. The second rule governs how the system partitions hyperbolically within the Planck mass gap. This logic governs how the system built from Planck boundaries coherently subdivides while remaining dynamically whole. Together, these 2 rules define a logic space, a constraint architecture, within which the constants of nature emerge as structural invariants, necessary expressions of the arena's internal structure. What we are uncovering here is not just a pattern in data. It is a map of how reality self-organizes from the inside out. These rules organize all 288 constants of nature into one coherent geometric language. Each constant falls into place as a precise expression of the same underlying logic. 5 Planck boundaries governed by 2 symmetry-based rules. The constants don't just reflect nature. They reveal the structural logic by which nature builds itself, and that logic, once seen, transforms the constants from a list of measured facts into a coherent grammar, a syntax of persistence woven by the geometry of the universe itself. These 2 rules pattern all 288 constants of nature, exactly, not approximately, producing the correct magnitude and dimension of each constant. This makes each constant of nature a precise expression of how the system partitions, how it folds, inverts, and repeats. The constants become fossils of that architecture, aspects of its internal powers of symmetry. What follows is a detailing of the discovery process that led to unveiling this pattern, and an exploration of the full pattern. We will examine each equation, its geometric components, the number it predicts, and how well this geometric logic fits the measured data. Then we will show that the geometric components of that structure map precisely onto the structural powers granted into the world by the hyperbolic figure-8 knot. This will lead us to identify the geometry responsible for sustaining the unitary internal logic of the Dirac equation. Then, we will use the structural features of that geometry to justify the 2 structural rules that exposed it, and discover the external geometry framing all the possible transforms available to it. This framing geometry gives the 5 Planck constants precise, geometric, structured homes. Finally, we will explore what it means ontologically, mathematically, and physically to access the geometric structure that governs how the world transitions from one state to the next while remaining coherently whole.